Thanks for listening to me speak, and thank you, Dan, for giving me the opportunity to speak. So today I want to talk about BP2 cooperations. Okay, so let me just sort of start with recalling some things. So like if you have a prime P, you have this ring spectrum called the Brown-Petersen spectrum. And its homotopy groups are very nice. They're this polynomial algebra over the p local integers on these generators v sub k, where the degree of v sub k is in 2 to the 2 times p to the k minus 1. So in particular, all the generators are an even degree. So the homotopy is an even degree. You can basically mod out by various ideals of the spectrum to get what are called the truncated Brown-Petersen spectra. So to BP brackets n, the nth truncated Brown-Petersen spectrum, that's obtained by taking BP and then killing off Vn plus 1, Vn plus 2, and so on and so forth. And then if you compute its homotopy groups, you're going to get what you expect to get. So you're going to get a polynomial algebra over the p local integers on these generators V1 up to Vn. All right. So here's, hold on. Okay, so when n equals 0, you just get the Eilenberg-MacLane spectrum on the p local integers because you killed V1, V2, V3, and so on.
And then there's the
when n is equal to 1 and p is equal to 2, then BP brackets 1 is actually the connective complex K-theory spectrum localized at 2. And the way this works is that so BP1, its homotopy groups are going to be the polynomial algebra over the p local integers on generator V1, and V1 when the prime is 2 is in degree 2, and that's corresponding to the bot element. When n is equal to 1 and p is odd, then BP1 is something else. It's the atom summand, and that is related to the complex K-theory spectrum, in that when you localize it at an odd prime, the connective complex K-theory spectrum splits as a wedge of suspensions of this atom summand. Now, the atom summand is going to be this polynomial, its homotopy is going to be a polynomial algebra on a generator V1, where V1 is in degree 2 times p minus 1. And so that's corresponding to the p minus first power of the bot element. Okay. So here's another example of a truncated Brown-Petersen spectrum. So this is, I guess, proved by Lawson and Naumann. So when n is equal to 2 and p is equal to 2, then they constructed this spectrum of topological modular forms of weight gamma 1, 3. And one of the things you can show is that that this spectrum is actually the same thing as the second truncated Brown-Petersen spectrum at the prime 2. Okay, so today's goal, though, will be to try and understand the cooperations algebras for some of these truncated Brown-Petersen spectra. In particular, we're mostly going to be focusing on the case when n is equal to 2. Okay, so just as a reminder, the cooperations algebra is going to be the homotopy groups of BP brackets n smashed with itself. Okay, so here are some examples of some known examples of these cooperations. So when n is equal to 0, then the cooperations algebra for BP bracket 0 is it's going to be a copy of the p local integers and then some torsion stuff. Now this torsion stuff is lying in, so a natural way to try and compute this cooperations algebra is through the atom spectral sequence. And this torsion stuff is all going to live in atoms filtration 0. So now when n is equal to 1, then you could also try and compute BP1 cooperations, and that was done by atoms in the later chapters of the Blue Book. And there he shows that you also have a splitting of BP1 cooperations into some nice stuff, what are called atoms covers, and I'll cover what that is later. But then, and also in his case, he gets a bunch of torsion stuff in atoms filtration 0. So in both of these examples, a natural approach is to use the atom spectral sequence, and that's the approach that we'll also use. So the atom spectral sequence is of this form for BP2 cooperations. So there are sort of two steps to understanding the cooperations algebra. Okay, so the first thing is you want to understand what the atom's E2 term even looks like. All right, and so that's sort of the first part. Hold on. So that's the first part. So what I'm going to try and show is that the atom's E2 term splits into a bunch of torsion in the atom's filtration 0, so in the 0 line of the atom's spectral sequence, and then everything else you get is going to be V2 torsion free and is going to reside in even degrees. And once you can show that, then you're going to get that the atom spectral sequence collapses at the E2 term. Okay. All right, so that's the first step. And so once you know that the atom spectral sequence collapses at the E2 term, then that just sort of leaves you to actually try and compute some X groups. And so that's sort of the second part of the talk, where I will develop some inductive computations. And sort of in summary, basically what happens is that the homology of BP2 is going to decompose into a direct sum of finite subcomodules called the Brown-Kittler subcomodules. And I'm going to sort of indicate how one would go about inductively computing those things. Okay, so more specifically, the results that I will talk about is this description of the atom's E2 term in terms of a V2 torsion free part and a torsion part in atom's filtration 0. And then I'll also sort of show how to do some inductive computations. Okay, so let's start with these structural results. So if you want to understand the atom's E2 term, then you need to, in the very least, know something about the homology of these BP brackets N. So let me tell you how you would describe the homology of these guys. So inside the Steenrod algebra, there are these important elements called the Milnor primitives. And for the most part, I'll be focusing at the prime 2, and everything I'll write will be for the prime 2. Sorry, is there a question? Anyway, okay. So you define these Milnor primitives by declaring Q naught to be the first Steenrod square, and then you define the nth plus first Milnor primitive to be the commutator of Qn with the 2 to the nth Steenrod square. So for example, Q1 is going to be the commutator of square 1 and square 2, and so you get, using the Adem relations, you're going to get square 3 plus square 2 square 1. Another thing I should mention is that in the Milnor basis, these Qn's are dual to zeta n plus 1 at the prime 2. Okay, so there are some important properties of these primitives, of these Milnor primitives. So the first being is that they're primitive elements in the Steenrod algebra. They also are going to be exterior elements, so they square to 0, and they all commute with each other. And so as a consequence of that, you are going to get that if you look at the subalgebra generated by the first n plus 1 Milnor primitives, that's going to be an exterior primitively generated sub-hop algebra. So I actually forgot to write that's going to be a sub-hop algebra. Okay. All right. So there are analogous things to say at odd primes as well, but I won't write that down. I should also mention that the dual. So the subalgebra En is a subalgebra of the Steenrod algebra. So its quotient will be a quotient of the dual Steenrod algebra, and it's going to be also an exterior algebra on primitive generators, and it's given as an exterior algebra over the zetas, these zetas. Okay. So now the main reason to bring these up is that you can describe the homology of BPN using these subalgebras. In particular, one can show that the homology of BPN is isomorphic to A mod mod En dual. And then if you explicitly compute what that is, say when the prime is 2, you're going to get a polynomial algebra on the squares of zeta 1 through zeta n plus 1, and then also zeta n plus 2, zeta n plus 3, and so on. And then you get a sort of similar sort of thing happening. You get a different sort of thing happening at odd primes. Okay, so because of this description of the homology of BP brackets N, you get a change of rings isomorphism for the atom's E2 page for the cooperations algebra. So and that's nice, right? Because now we just have to compute X over a finite hop algebra. But then the question still remains: is what is A mod mod En dual as a co-module over En dual? Okay, and now so I should mention so A mod mod En dual is going to be so it's naturally a sub algebra of the dual standard algebra. And so as a comodule over the dual standard algebra, you just get its coaction by restricting the coproduct on the dual standard algebra. So this is the coproduct for the dual standard algebra, as I'm sure you guys have seen before. And so here, let me indicate how you actually sort of derive the E2 star coaction then on A mod E2 dual. So what you do is, so like I said, so you basically restrict this coproduct to A mod E2 dual. Now the thing is that E2 dual is a quotient of the dual standard algebra. So you just project onto E2 dual on the left factor, and that's how you compute this coaction. And so if you work that out, so effectively what that means is that you look at the, say for zeta k, you just look at the coproduct for zeta k, and then you kill off zeta 4, zeta 5, zeta 6, and so on. And so, and the result of that is that you get this formula for the coaction. And then you also end up getting that the squares on the first three zetas are going to be comodular primitives. Okay, so right, so this is and then I should also mention that A mod E2 dual is a comodular algebra. So once you know the coaction on the zetas, then you just know the coaction on everything. Okay. When Adams computed the cooperations algebra for BP brackets 1, he wanted to actually use a module structure. He wanted to think of everything as a module over E1, and we're going to do the same thing. So I actually want to regard A mod E2 dual as a module over E2, and it's related to the coaction in the following way. So here again is the formula for, say, the coaction on zeta k. So remember that, say, Q naught is dual to zeta 1. So what this coaction formula is telling us is that Q naught on zeta k is going to be zeta k minus 1 squared. Zeta 2 is dual to Q1, so Q1 on zeta k is going to be zeta k minus 2 to the 4. And Q2 is dual to zeta 3, so Q2 of zeta k is zeta k minus 3 to the 8. Okay, so this just derives the entire, so this just tells us what the action is on these zeta k's, but then you can derive, but then you can also show from this that the action by the QIs is going to act as a derivation. So actually, you just derive all the action from these basic formulas, and then using the Leibniz rule. And then again, there's sort of a similar thing that works out at odd primes. So one of the reasons for doing this, is that there's a really important invariant for studying the X groups of modules over an exterior algebra, and this is called the Margolis homology. So let me remind you what the Margolis homology is. So suppose that you have an exterior algebra, EX, and you have a module over this exterior algebra. Then you can consider the multiplication by X map on the module. And because it's an exterior element, it squares to 0. So in particular, you can regard it as a differential. And so you can turn P into a chain complex. And so you can take its homology. And that's what we call the Margolis homology. And so in particular, the Margolis homology with respect to X is just the kernel of the multiplication by X modulo the image of multiplication by X. Okay, so now in our case, though, we actually have three distinct exterior generators, right? We have these three Milnor primitives that we're thinking about. So we need to keep track of the Margolis homology groups with respect to each of these Milnor primitives. All right, so here's the here's the sort of the main reason why one would even think about Margolis homology, and that's because they detect stable equivalence for E2 modules. So two modules over E2 are said to be stably equivalent if they're isomorphic to each other after summing up with some free submodule. Oh, sorry, with free E2 modules. Okay, so in particular, if you have, because the X groups of free E2 modules are only in X to 0, if two modules are stably equivalent, that means their X groups are going to be the same above the 0 line. All right, and so that's sort of one of the reasons why we want to consider Margolis homology in the first place. So in particular, there's this theorem of Margolis that says that a module over E2 will be free if and only if all of its Margolis homology groups vanish. Okay, and as a consequence of that, you have that if you have a map of bounded below E2 modules, then F is a stable equivalence if and only if it induces an isomorphism in Margolis homology. Okay, so here I'm just recording the Margolis homology groups for a mod E2 dual, and these basically just come from the Kunis formula. So the Margolis homology is defined over a field, so that means it has a Kunith isomorphism. And you basically just compute this using this Kunith isomorphism. Basically, actually, I have some notes for this, I think. Right. So here's an example of how you go about computing the Q-naught Margolis homology for a mod E2 dual. So first, from our formulas, we know that any of the powers of zeta 1 squared, they neither support or are hit by a Q-naught multiplication. And the same goes for the zeta 2 squared. So you have all of these sort of trivial little Q-naught chain complexes. Now, and then when k is, say, greater than or equal to 3, I also have these sort of short little Q-naught chain complexes. So for example, Q-naught of zeta k plus 1 is zeta k squared. So I regard that as a little chain complex. And I also have this little chain complex, zeta k squared, zeta k plus 1, hits zeta k to the 4, and so on. And so now what happens is that a mod E2 dual is actually the tensor product of all of these small chain complexes. And each of these small chain complexes has it's really easy to compute their Margolis homology. And then because Margolis homology has a Kunith isomorphism, all of these small little chain complexes disappear, and then all you're left with is these powers of the zeta 1 squared and zeta 2 squared and their tensor products. And so that's how you end up with this polynomial algebra on zeta 1 squared and zeta 2 squared. And it's the same story for all the other Margolis homology groups. Okay. All right. So now what I want to talk about is this question. So in the examples I mentioned before for, say, BP0 cooperations and for BP1 cooperations, you had all of this torsion that was concentrated in Adams filtration 0. Okay, and so what we're going to try and do is we're going to try and capture as much of that torsion as possible. So one question that you should ask yourself is, what is the source of these? What is one source of the torsion in X0? And the answer for that is free E2 submodules of a mod E2 dual. Okay, so now observe that if you have an element of a mod E2 dual, then it will generate a free submodule if and only if the action by the 3 Milnor primitives is non-zero. Okay, right. And so what you want is a nice criterion for sort of determining when it's even possible for an element to have the action of all 3 Milnor primitives on it possibly being non-zero. And so that's why I'm going to introduce this notion that sort of helps to describe when this may or may not happen. And that's this notion of length. So if you have a monomial, as depicted above, then its length is just the number of odd exponents occurring in the monomial. Okay, and now if you have a generic element of a mod E2 dual, you say that it has length L if it is a sum of monomials, all of whom have length L. In which case we'll write Lx equals L as well. Okay. So for example, as some examples, zeta k plus 1 has length 2 because both of the generators there have exponent 1. But on the other hand, you have zeta k squared has length 0 because 2 is an even number. Sort of another example is zeta 4 squared, zeta 7. So this has length 1 because the exponent for zeta 4 is 2, which is even, but the exponent for zeta 7 is 1, which is odd. Okay. Are there any questions so far?
Questions?
Okay. If not, I'll continue. But anyway, so notice one thing to notice is that so as I mentioned before, the QIs are derivations, and we're also working in characteristic 2. So So because the length 0 monomials are just those things, are those monomials which have all even powers, those things are necessarily killed then by the action by these Milnor primitives. Another thing you can say about the action by the Milnor primitives is this. So if you have an element of A mod mod E2 dual of positive lengths, so again, that means that it's going to be a sum of monomials all having the same lengths, then the length of Qi of X is going to be L minus 1. So the action drops length by exactly 1. So here's an example to indicate what I mean. Okay, so Q naught of zeta k plus 1. So you apply Leibniz rule, and you're going to get zeta k cubed plus zeta k minus 1 squared zeta k plus 1. Now, both of these terms have length 1. In the case of zeta k cubed, 3 is odd, so that has length 1. And in the case of zeta k minus 1 squared zeta k plus 1, well, the only odd exponent there is for zeta k plus 1. So that also has length 1. So you have that Q naught of a length 2 guy is going to be a sum of length 1 monomials. And so we say that it drops the length by 1. Okay. So now remember I said that an element of A mod mod E2 dual will generate a free E2 submodule if and only if the action by all three of these Milnor primitives is non-zero. So now assuming that X has a length, then this means that, so if Q naught, Q1, Q2 of X is not 0, then that means it has, say, length 0 at worst, okay? And so that means that by the previous proposition, that means that X has to have length at least 3. So what this suggests, so if you're trying to capture as much of the torsion in Adams filtration 0 if you're trying to capture as much of that as possible, it makes sense to consider the following submodule of A mod mod E2 dual. So consider the submodule S, which is generated by all of those elements of A mod mod E2 dual whose length is at least 3. So the idea is that, so it's certainly the case, based on all of our observations thus far, it's certainly the case that S contains all of the free submodules of A mod mod E2 dual, okay? But what is maybe not clear is that it doesn't capture any sort of other stuff. So you want to check, what you would like to check is that it only has, that it's only capturing what you would like to know is that it's only, that it is actually a free submodule. And so it's only capturing torsion elements in X0 arising from free submodules. And that happens to be the case. That's something that one can prove, is that the Margolis homology of groups are trivial. And therefore, by that theorem of Margolis, S is actually going to be a free E2 module. Okay. Consequently, what this means is that, so you can mod out by S, all right, and you get a quotient Q. Okay, so I have the short exact sequence. So because the Margolis homology of S is trivial, this means that the natural projection map induces an isomorphism in Margolis homology between A mod mod E2 dual and Q. Okay, and so that means in particular then that the X groups for these two things are the same above the 0 line. And so now what we want to do is study the X groups for Q. And this is actually a really good move because Q is significantly smaller than A mod mod E2 dual. Okay, so remember I'm trying to prove this theorem that the Adams E2 term breaks up into some stuff on Adams filtration 0 and also this V2 torsion free stuff. And so my hope is that the X groups for Q will be V2 torsion free. So a natural way of trying to show something like that is to use the V2 Lockstream spectral sequence. So that's a spectral sequence of the following form. So I've suppressed the indexing, but this is actually a tri-graded spectral sequence, right? So 2 of the gradings come from X, and the third grading comes from the power of V2, okay? And if you use Adams indexing, all the differentials for this are going to look like D1 differentials. Okay. Now, one other reason why this is a really useful move is because it's not so hard to compute X of modules over E1. And I mean, this was like studied, these guys, like the X groups of these things were studied by, say, Adams and Priddy in their paper on uniqueness of BSO, where they talk about these things called lightning flash modules. And as it turns out, Q is actually more or less a direct sum of lightning flash modules. So I just want to explain what lightning flash modules are in case you haven't seen it before. So I've drawn a picture of a lightning flash module over here. Okay, so basically it's just alternating between a Q1 action and a Q0 action. So you have this Q1 action that hits X, and then that thing that hits X has a Q0 action. And then that Q0 of this thing also is hit by Q1 of something, and then so on and so on. So you have this alternating between Q1 and Q0 and Q1 and Q0. Okay, so now these guys are these lightning flash modules are characterized by the fact that their Margolis homology groups are one-dimensional, more or less, at least stably. So for example, you can see here that the Margolis homology of this lightning flash module with respect to Q0 is just this one-dimensional vector space generated by X. And so, for example, you see this because everything in the top row supports either a Q1 or a Q0 multiplication. So they don't appear in the Margolis homology. And everything in the bottom row is hit by Q0 except for X. So that's why only X appears in the Margolis homology. And that's the same. It's the same that goes for Q1. Okay, so more or less the point is that if you know the Margolis homology groups for this thing, you can actually compute its X groups. And in this case, what I've drawn is, so this guy is going to be a fourth Adams cover of BU. Okay, so let me explain what I mean by an Adams cover in a practical sense, at least. So practically speaking, once you the fourth, say if the fourth Adams cover of BU is, you just draw the BU pattern, and then you go up 4 rows. Okay, and then you draw a new line on the 4 line and call that 0 now, and then everything above that is X of L. Okay, and that's what we call an Adams cover. And now in particular, the point is that what Adams cover you're taking is uniquely determined by the degrees of the Margolis homology classes. So the fact that X is in degree, say 2, and Y is in degree 4, 6, 8, 10 sort of uniquely determines the fact that this is a fourth Adams cover. Okay, and then so the point, and so notice here that so V1, so this line of slope 1/2 is a V1 multiplication. Okay, and V1 has degree 2. So notice that so long as X is an even degree, the Adams cover associated to it is completely with an even degree. Okay, and now the thing is that let's see, I recorded this. So let's see. So the Margolis homology, say the Q0 Margolis homology, this is a polynomial algebra generated by zeta 1 squared and zeta 2 squared. So this is entirely in length 0, and also in particular, it's entirely in length in even degree. So that means that, so basically from this you can show that the X groups over E1 for Q are completely concentrated in even degree. And now and also V2 is, so the degree of V2 is 6. So the entire E1 term of this V2 Boxian spectral sequence is completely concentrated in even degree. And because the differentials all look like D1 differentials, that basically means that the spectral sequence has to collapse. And so this means that the X groups for Q over E2 are V2 torsion free. Okay, so we're basically almost there in terms of the structural results. Right. So remember that I have. So I have to recall this fact that so if you have a finite Hopf algebra over a field, then it turns out that being injective and being free and being projective are all the same. And remember that I have I have the short exact sequence near the bottom here. So A mod mod E2 dual fits in between S and Q. And now because S is free and therefore injective, this short exact sequence splits. And that's how I derive this direct sum decomposition for A mod mod E2 dual. And so in particular, you can apply X to this. And I claim that this gives us our desired decomposition on X. In particular, X of S, we've already shown is all in, and S is free, so that means its X groups are concentrated in filtration 0, Adams filtration 0. And we've also just shown that the X groups for Q are concentrated in even degree and are V2 torsion free. And from this, you can derive that the Adams spectral sequence for BP2 cooperations collapses at the atom's E2 term. Okay, so that concludes the first part of my talk. Are there any questions before I move on to the inductive calculations?
Yeah, this is Nicolas. I have a question.
Oh yeah, sure. Go ahead.
So in your picture about lighting flashes, the only one that appeared were the Adams covers of the units in the category of E2 modules.
Mm-hmm.
But classically there are two kinds of lighting flashes: the one that either begin with a Q0 and end with a Q1, or begin with a Q1 and end with a Q0. But there is also the type that begins with a Q0 and ends with a Q0, and this one does not have the property that it has a one-dimensional Margolis homology with respect to both Margolis homology. So is there a reason why this does not appear in the picture?
So I guess the point is, so I think the latter ones you talked about, so the ones that I all talked about are the ones that are in the Picard group for E1.
Mm-hmm.
Yeah, and so like class, yeah, so the point is that you can rewrite Q as some stuff where the Margolis, yeah, let's see, what do I want to say? So let me say it for BP1 instead, where it's a little easier to say things. So in the case of BP1, like if you actually look at the Margolis, so the thing is that I haven't mentioned it yet, but there's a weight on these things. Okay, so for example, in BP1, so I'm going to talk about it a little bit later, but so zeta k is declared to have weight zeta 2 to the k minus 1, and that puts so that allows you to sort of put that induces a weight. So sorry, hold on. So you have this you can put this weight on, say, A mod E1 dual. And that allows you to also put weight on the Margolis homology group. So now if you look at any particular weight for A mod E1, the Margolis homology groups in that particular weight are necessarily one-dimensional.
Oh, okay, I see. Thanks.
And so that's why those appear in the one case. It's a little bit, so you can't immediately draw that conclusion for Q. There's a little bit more, there's some stuff I suppressed in my arguments, but you can sort of reduce to the case where the Margolis homology groups are going to be one-dimensional in any particular weight, and then reduce to this to these invertible E1 modules, and then get these Adams covers. Yeah.
I see. So you use at some point that A mod E2 is a direct sum as E2 module of modules of the form A mod A2, and then play with this one.
Not quite. Yeah, I mean maybe. Yeah, so maybe we can talk about it like a little bit. It's a little bit more complicated than that, I suppose. But
okay.
Yeah, but let's talk about it maybe after. Any other questions before I move on? Okay, so if not, let me continue. Right, so now we have some sort of general structural results, but the question is, how do you actually compute these things and actually present them? So now let's move on to inductive calculation. So here we are. So let me just talk about weight really quick. So Mohold and various things that he studied, he sort of put this sort of weight function on the monomials of A mod E2, or rather just on the monomials of the dual Steinrod algebra. And the way he defined them is by, he declared the weight of zeta k to be 2 to the k minus 1. And then he extends multiplicatively, so that the weight of the product is just the sum of the weights of the constituents. Okay, so now, so the main observation for us will be that the weight is preserved by the action of E2. So here's an example to indicate this. So if you look at Q1 of zeta k, that's zeta k minus 2 to the 4. Now the right-hand side, so what is the weight of the right-hand side? Well, the weight of zeta k minus 2 to the 4, well, that's 4 times weight of zeta k minus 2. That's 4 times 2 to the k minus 3, by our definitions of weight, and that's 2 to the k minus 1, because 4 is 2 squared. And so therefore, and that's exactly the weight of zeta k, okay? So this example illustrates this general phenomenon that the action of E2 is actually preserving the weight. Okay, so it makes sense then to consider the following. So look at the F2 linear span of the monomials of A mod mod E2 dual, where the weight of M is exactly 2 times K. I'm writing down 2 times K because all weights are divisible by 2 in A mod mod E2 dual. So by the previous observation, this guy is defining an E2 submodule of A mod mod E2 dual. And because everything has a weight, we have that A mod mod E2 dual actually decomposes as a direct sum of these M2K guys. Okay, so I have some pictures to show you. Right, so here are some examples of these M2 things. So for example, so M21, that's the span of all the monomials of weight exactly 2. Now, the only monomial of weight 2 is zeta 1 squared, as it turns out. Because zeta, so the next monomial that appears inside A mod mod E2 dual is zeta 2 squared, but the weight of that is 4, so it doesn't make an appearance in the M21. Now in M22, so that's the span of the monomials of weight 4. So that's going to have a zeta 1 to the 4th and a zeta 2 squared. M23, that's the monomials of weight exactly 6, and that's zeta 1 to the 6th. So you get zeta 1 to the 6th and zeta 1 squared, zeta 2 squared. And now I should say that in the case of M21, M22, and M23, all of these are trivial E2 modules. So the action by the Milnor primitives is trivial in this case. On the other hand, so the first interesting example sort of shows up with this M24. So if you just write down what the monomials that appear in M24, so that's the monomials of weight 8. So what you get is zeta 1 to the 8, zeta 1 to the 4, zeta 2 squared, zeta 2 to the 4, zeta 3 squared, and zeta 4. And now there's some actual interesting action by the modules over E2. And so here in this picture that I've drawn to depict M24, so the short straight lines represent multiplication by Q0. The curved lines represent multiplication by Q1, and these long square lines represent multiplication by Q2. Okay, and so this is just coming from the formulas that we've indicated before. So you get this sort of weird I don't know how to describe this pattern, but you just get this pattern, and then you get this sort of trivial submodule zeta 1 4 zeta 2 squared sort of sitting inside as well. Okay, so so now these things are all going to be finite dimensional over F2, which is good because it's preferable to compute X groups of finite dimensional things. Now these things happen to be related to the Brown-Gittler subcomodules for connective complex K theory. So I need to explain what those are. So as a reminder, what is the homology of connective complex K theory is A mod mod E1 dual, and that's this polynomial algebra on the squares of zeta 1 and zeta 2, and then also with zeta 3 and zeta 4 and so on. So the jth BU-based Brown-Gittler subcomodule is defined to be the F2 linear span of the monomials of A mod mod E1 dual, with the weights where the weights are less than or equal to 2J. Okay, so let me draw some pictures of these guys. Okay, so here's a copy of here's a BU1. So that's the monomials of the homology of BU, which are of weight less than or equal to 2. So one has weight 0, so it makes an appearance, and zeta 1 squared has weight 2, so it makes an appearance. But that's it. Now BU2, that's going to be the span of the monomials of weights less than or equal to 4. So in for that case, you get 1 zeta 1 squared, zeta 1 to the 4, zeta 2 squared, and zeta 3. And now if you try and draw this as an E2 module, this is the picture that you get. And so notice that these two things are looking the same. And that's not an accident. That's because this is actually part of a more general phenomenon. So you can write down this map from A mod mod E2 dual to A mod mod E1 dual. But where you take zeta k to zeta k minus 1. And I guess I'm implicitly saying that zeta 0 is 1. So if you restrict this map to a particular weight in A mod mod E2 dual, you can argue that you can argue that that's going to actually just give you one of these BU Brown-Gittler subcomodules. In particular, the jth M2J thing is going to be the same as an E2 comodule to a 2J fold suspension of this floor of J divided by 2 BU-based Brown-Gittler subcomodule. So we want to compute, so we want to figure out a way to compute X of these things. So we've just, I mean, it's an equivalent thing to try and compute X of these BU Brown-Gittler subcomodules. Okay, so now what I'm going to try and sort of indicate is a method that sort of originated, I guess, well, I mean, a method I sort of took from these papers by Behrens, Hill, Hopkins, and Mahold, and Behrens, Ormsby, Stapleton, and Stoyanowska. And so in those two papers, they had to look at the Brown-Gittler subcomodules based upon connective real K theory, so the BO-based Brown-Gittler subcomodules. And it's the same sort of thing. You put so the homology of BO is A mod mod A2 dual, sorry, A mod mod A1 dual. And you can put, again, a weight filtration on that thing. And then you can sort of define BO Brown-Gittler subcomodules in the same way by weight less than or equal to 4J in the case of BO. And then what they do is they produce these exact sequences relating BOJ to BOK for smaller values of K. And I do essentially the same thing. And once you have these exact sequences relating BUJ to BUK of smaller K, that sort of gives an impetus to actually do some sort of inductive method of computation. So these are the exact sequences that you can come up with. Oh, sorry, there's a typo here. So notice in this first exact sequence, there's this appearance of this underlying BP2 2J-1 tensor E2 mod mod E1 dual. So this underline BP2 thing is the BP2 Brown-Gittler subcomodules. And you're defining, one defines it sort of in an analogy with the BU Brown-Gittler subcomodules. So BP2 sub K is supposed to be the span of the monomials in A mod mod E2 dual. So that's where there's a typo. It's supposed to be monomials in A mod mod E2 dual of weight M less than or equal to 2J. Okay. Right. So yeah, so anyway, so in both of these sort of exact sequences, the thing you're really wanting to compute is the X groups for BU2J or BU2J plus 1. And so we regard these exact sequences as giving us spectral sequences converging to X of these desired X groups. And they look like this. Okay, so in the case of you're trying to compute X of BU2J plus 1, you get an E1 term whose which is coming, you have an E1 term whose, which is the direct sum of X over E2 of this BUJ tensor BU1, and then also X over E1 of these, I'm sorry, there's a missing underline, but the X over E1 of BP2 2J minus 1. So the fact that there's this X over E1, it's coming from the fact that in these exact sequences, you have BP2 2J minus 1 tensor E2 mod mod E1 dual. So then you can use a change of rings to say that X over E2 of this thing is actually just X over E1 of this BP2 Brown-Gittler subcomodule. Okay, and so you get an analogous sort of spectral sequence for the even ones. And you get and then I've also sort of written down some suspensions here. These suspensions are coming from the suspensions in this proposition, basically, because I want to give names. So my goal is to sort of is to actually write down some generators, and I want to give names to these generators that come from A mod mod E2 dual, not from A mod mod E1 dual. So that's why I'm keeping track of these suspensions. Okay, so part of this procedure, that part of this inductive method of computation means that I have to compute X over E1 of BP2 2J minus 1. So let me sort of indicate sort of what's going on there. So BP2J decomposes. So A mod mod E2 dual splits as a direct sum of these M2Ks. Now BP2J is just the stuff in A mod mod E2 dual of weight less than or equal to 2J. So you get a similar decomposition in terms of the M2Ks. All right. And then I can use this reduction map to relate these two suspensions of these BU-based Brown-Gittler subcomodules. And now there's sort of an analogous reduction that allows you to go from BU Brown-Gittler subcomodules to integral Brown-Gittler subcomodules. Okay, so I have this. Now the reason why I want to know this is because I know how to compute the X over E1 groups for integral Brown-Gittler subcomodules. In particular, the Margolis homology of these integral Brown-Gittler subcomodules are both one-dimensional. So I know that their X over E1 groups are going to be Adams covers. And you can explicitly write down these Adams covers based on the Margolis homology. Okay. So now the other thing I'm going to do, so to sort of simplify the work, so you want to know, you kind of just want to keep track at first of like where the Adams covers starts. So let me sort of go back to a previous picture. So like look at this Adams cover that I have over here. So if you have this Adams cover, then you can reobtain the BU pattern by inverting V0. And then once you invert V0, this whole thing just becomes generated by X basically. Okay, so upon inverting by V0, you're just keeping track of the starting point of this Adams cover for these lightning flash modules. And so that's what I'm doing with this lemma over here. I'm just keeping track of the starting points for these Adams covers. So anyway, this lemma is just a Margolis homology computation basically. Oops. Okay. So all right. So we have this way of naming the generators for BP2 2J minus 1. But we really want to know what to name these generators within A mod mod E2 dual. And so I need to say something about, right, so I'm kind of running out of time, but so let me just say that these generators, these generators that I've written down over here, when you actually sort of follow through the various maps and the exact sequences that I wrote down, the names that are really associated to these generators are given below by these things. So you sort of increase the lower index by 1, and then you add on a power of zeta 1 to make sure that the weight of this thing is going to be 8j plus 4 epsilon. Okay, so this is sort of like the new input at the 2j plus epsilon stage. Okay, but you also have these inductive terms, okay, that are coming from the lower BUJs. So you need to know what generators these are determining. Okay, so it turns out that if you follow through, so if you inductively suppose that the generators for the X groups for sigma 4j BUJ are given by this, then when you inductively input them into the next stage, you're just increasing the bottom index by 1. And then in the case of the odd guy, you have to also multiply by zeta 1 to the 4 and zeta 2 squared. Okay, so that's how you can name the generators, and then you also have to resolve some hidden V2 multiplications. So in the case when you're computing X of these BU2Js, there was a sort of extra summand coming from a BUJ minus 1. The whole purpose of that guy was just to receive V2 multiplications from generators arriving from this BP2 term of the form zeta 1 to the 4th, zeta 2, 2i2, zeta 3, 2i3. And then you can sort of resolve all the other hidden extensions, hidden B2 extensions, using the following fact. So you kind of, through some other means, you know that you have these relations, as I've indicated over here. And you just sort of, yeah, so that sort of deals with the other hidden B2 extensions on the other generators arising from the BP2 term. And I think, yeah, so I think that's where I'll end for today. So thanks for listening, and yeah, so do you guys have any questions?
I'm gonna unmute everyone so we can thank him. Okay, and now I'm going to go ahead and mute everyone again, and then I will unmute you, Dominic. Okay, other questions for Dominic?
Hey, Dominic, it's Mark.
Oh, hey, Mark.
Hey, so this was all at the prime too.
Yeah.
So what's the prospects for the odd primes?
So the structural results appear to go through without a hitch, and they're essentially the same form. It's just, I mean, so that the proof, it really is the same. You just make the usual translation that like zeta tau n is like zeta n plus 1, and zeta n squared is zeta n or whatever. So that part is easy, but but the problem is it's a little tricky. So it's sort of work in progress, but the harder part is sort of developing the analogs of the these short exact sequences. So what appears to be happening, what appears to happen is that you have the same. So what it seems to happen, instead of having two exact sequences, you're going to have a z mod p number of exact sequences. And so what you have to do is you're going to try and compute BU. Sorry, you're going to try and compute. So you replace BU with L Brown-Gittler subcomodules. So you want to try and compute. You want an exact sequence to help you understand L sub pj plus k, where k is between 0 and p minus 1. Yeah, and so actually most of those are going to be, I think basically you're going to get p minus 2 many exact sequences with 4 terms in them, and then you're going to get one which is also a short exact sequence. But I'm kind of, at the moment, I'm getting really confused about the suspensions and stuff.
Gotcha.
So, but I do expect there to be analogs of these exact sequences.
Cool.
Other questions?
Yeah, this is Nicolas. So there is this 20 years old result by John Palmieri, which says the following: if you have an A module, which is acyclic with respect to Q2, then he shows, using the action of the Stirnod algebra on X groups, that actually it has to be also free on Q1, Q0, and this operation P21. So can this be used to, apply it to, for instance, S, if S is a sub A module, to show directly that it's free over E2 and maybe A2, or maybe can this be used for higher BPNs?
I don't know that result, but that's actually really interesting. So you're saying that. So are you saying that, like, for example, in the case of S, if you could show that its Q2 Margolis homology was trivial, then it would just follow for the rest?
It's some kind of it's like a chromatic filtration for A modules. So you have to be sure that it's actually a sub A module, and then if something is free over Qn, it will automatically be free over the whole thing.
Yeah. So I guess the hard part would be. I guess the hard part, I don't know off the top of my head if S is a sub A module at the moment, and I mean, I'd have to think about it, but I actually don't think it will be, for example. So for example, so the problem is, like, so for example, like, I don't want to say something stupid, but I don't expect it to be a sub A module, unfortunately.
Okay.
So
maybe could it be a sub A2 module? Maybe it's sufficient.
Yeah, for A2, maybe that might actually be possible. That one I'd be more I would be more willing to believe that could actually happen, that it could be an A2 submodule.
Okay.
Yeah, it's really that's really interesting. I didn't know about that result, Nicola. And thinking about it for X over AN, it makes you think maybe there's like a finite analog, like a finite filtration. That's it. Fascinating.
I feel
What's
that
the name
some
of the
these
paper?
results- Sorry?
Well, what's the name of the paper? Just out of curiosity.
Oh, I can send it to you. That's a result I heard about really recently, and it seems that it had been somehow slightly forgotten. It was when he was attempting to prove a thick subcategory theorem for A modules, and so he came up with this sort of chromatic filtration. He called it slope supports, and yeah, and you have those results that are really powerful, but I didn't see much people use it. I can send you the paper.
Oh yeah, that'd be great.
Send it to me too, Nicola.
Sure, I will.
All right, thank you.
Okay, other questions? Okay, if not, let's I'll unmute everyone. We can thank Dominic one more time. Thanks very much. And we'll see you all in 2 weeks for Justin Noel for the last talk of the season. Thanks. Bye. All right.